Hello, welcome to Basics of Finite Element Analysis, and in today's lecture what we will discuss is another set of equations known as hyperbolic equations. And the important thing about these equations is that they involve second order derivatives in time. So, in case of parabolic equations, which we have discussed in last several lectures, 2-3 lectures, we figured out how to handle first order derivatives of time and how to integrate equations, ordinary differential equations in time of first order using the alpha family of approximations. What we will do today is hyperbolic equations, and as these equations have second order of derivatives in time, we will use a different integration method known as Newmark family of integration to convert these partial differential ordinary differential equations, second order ordinary differential equations in time to algebraic equations. So, as I mentioned, what we are going to discuss today are hyperbolic equations. And the condition for a hyperbolic equation is that C2 should not be equal to 0. So, what is C2? So, C1, C0, C1 and C2 are listed in our original differential equation. So, this should not be equal to 0 because that is what gives us the second order derivative in time. So, but in context of today's class, so this is the condition, but we will also additionally assume that C1 equals 0, and that implies m prime equals 0 and not m prime, m1 equals 0. Physically what it means is that this term is 0 in the special type of hyperbolic equations which we will discuss today. And physically what this means is C1 is some constant times du over dt. If u is displacement, then du over dt would be velocity, and so C1 times velocity is in several systems representative of viscous forces or damping forces. So, in context of the discussion we will have in our class today, we will say that the damping or viscous effects in our system are negligible or they can be ignored. So, for such a system, the equation, this entire equation, it essentially reduces to this form. So, that is the hyperbolic equation, and how we arrive at this equation we have seen earlier through our regular method of spatial approximation. So, now our aim is that we have to first integrate this. So, in this equation we have m2 which is the mass matrix, k which is the stiffness matrix, and f which is the force vector. So, all these things are known, and we have to now express or find out the value of u at different nodes for all periods, for all time instant, and our aim will be to get that information by integrating it, so that we get a set of algebraic equations. So, those algebraic equations we will get through an integration scheme known as Newmark scheme. So, we get it through Newmark family of approximations for u dot and the second derivative, which is u double dot, and the relations are u s plus 1 equals u at time step s plus delta t times u dot at time step s plus delta t square over 2 times u at time step s plus gamma. So, gamma is a different term I have introduced, and we will explain what that means. And similarly, the velocity or the first derivative in time at step number s plus 1 equals u at time step s plus u double dot at time step s plus alpha times delta t. So, an alpha is between 0 and 1, and so is gamma. Alpha could be a number between 0 and 1, and so could be gamma. So, the question is, so what this family of approximation helps us do is, it helps us calculate u and u dot at time step s plus 1. On the right side, we know u dot and u at time step s. We also know the value of delta t, we can choose it. We also know the accelerations at time step s, but we do not understand how to calculate u at s plus gamma and u at s plus alpha. Okay. So, this is actually the second derivative. So, to calculate u double dot at s plus gamma or s plus alpha, we use another formula prescribed in the same for the same family of approximations, and it says that the second derivative of u at s plus theta. Now, theta could be either alpha or it could be gamma. So, we will give a relation for this, and we can use this relation to calculate u double dot at s plus gamma and u double dot at s plus alpha. So, u at s plus theta equals 1 minus theta times u double dot at s plus theta times u double dot at s plus 1. So, use this to compute u s plus gamma and u s plus alpha. So, if I plus theta is equal to alpha, then I get u s plus alpha. If I get theta equals gamma, then I get s plus gamma. Now, the next question is, what should be the values of theta and alpha and gamma? Okay. What should be the values of theta and gamma? So, for that we will develop a table. So, alpha and gamma, name of the method and stability. So, in the first case, alpha is equal to half, gamma equals half. This method is known as constant average acceleration method, and the stability thing is that it is always stable. So, I do not have to worry about delta t, it will always be stable. If I take delta t as very large, it may become inaccurate, but it will not become unstable. So, I can use this method, or I can also use alpha equals half, gamma equals 1/3, and this method is known as linear acceleration method. This is conditionally stable. Another set of alpha and gamma could be half, gamma could be 0. This is called central difference method. This is also conditionally stable. Another option could be 3/2 and 8/5, and this is known as Galerkin method. So, one small error which I made was that these conditions are not accurate. Alpha, they can exceed 1, but they have to be more than 0. So, in this Galerkin method, this is all again stable, and another value could be 3/2 and this is 2. This is known as backward difference method. And this is also stable. So, this gives us the overview, and what it says is that if I have to solve this equation m2 times u double dot plus k times u equals f, I can express u double dot, which are the second order derivatives in time, using these two relations. Okay. I mean, I have to move this using these two relations, and then using and once I do that, I will be able to convert this equation into a set of algebraic equations. So, and while using these, I have to choose an appropriate value of gamma and an appropriate value of alpha, and I have several choices, and out of these 5 choices, 2 are conditionally stable and the remaining 3 are always stable. In this case, the conditional stability is when, so what is the conditional stability? When delta t is less than delta t critical, and this equals omega square by 2 times alpha minus gamma, the whole thing raised to the power of half, okay, where omega is maximum eigenvalue of system. So, once again, first if we have to use these two methods, linear acceleration or central difference method, which are conditionally stable, we have to ensure that the time increment is less than time critical, and that equals square root of omega square divided by 2 times alpha minus gamma, and omega is the maximum eigenvalue of the system. So, I have to calculate the eigenvalues by putting f is equal to 0 in this equation. So, next what I will do is, I will straight away write the solution of this equation, because you know the philosophy and the theory, and at this stage for purpose of brevity we will straight away write the solution of this equation, and the solution is k hat. So, this is for the hyperbolic equation where the damping is also 0. So, k hat evaluated at s plus 1th time step times u evaluated at s plus 1 time step equals f corresponding to s and s plus 1, and here k hat evaluated. So, this is the equation we have to solve. So, if I can calculate the left side vector, the right side vector f, and on the left side if I can calculate k hat, it gives me an assembly element level equations. I can assemble that and do all the boundary conditions and initial conditions application, and then I will be able to figure out u at s plus 1th time step. Okay. But we have to define what are k hats and f at s and s plus 1. So, k hat is equal to k evaluated at s plus 1th time step plus a constant A 3 times mass matrix evaluated at s plus 1 time step. And typically this mass matrix does not change with time. So, we do not have to worry, I mean once we calculate it, it remains the same. But the force vector, it certainly changes with time, and f corresponding to s and s plus 1 is defined as f evaluated at s plus 1th time step, and we know how to calculate this, plus m at s plus 1 multiplied by A 3 u s plus A 4 u dot s plus A 5 u dot s. Okay. Now, as I said, typically mass does not change with times. So, this is more or less fixed. So, we do not have to, once we calculate it, it remains same in a lot of situations for all the things. Force, we know that this depends on f and q's, right, and if we know the values of q's from the last time, and also we know that the f force vector is a known function. So, I can calculate this function also, this vector f also. But these terms have to be known to calculate f at s comma s plus 1. Okay. So, I have to know the position, if u is the position, if u represents position, then I have to know u, that is the position at last previous time step. I have to know u dot or velocity at previous time step, and I have to know acceleration at previous time steps. Oh, by the way, A 4, I have to define A 3, A 3 equals 2 over gamma times delta t square, A 4 equals 2 over gamma times delta t, and A 5 equals 1 over gamma minus 1. So, all these A 3, A 4, A 5, they are known, because this gamma is known, delta t is known, everything. But I have to know the solution at the previous time step. Now, when I solve for this equation, how do I do that? I first do element equations, then I do assembly, then I do boundary conditions, then I do boundary conditions, but I have to know, to solve for the next time step, I have to know the solution at the previous time step. So, I have to know, so what that tells me is that I have to know, and then I apply ICs, and I have, so what are the 3 ICs? I need u, u dot and u double dot. Okay. Now, these two, they have to be explicitly known. This u double dot at the last time step, I can calculate. So, for instance, at time, so this is actually calculated at time t is equal to 0. For instance, at time t is equal to 0, first thing what we will do is, we will calculate u, and how will we calculate u? We will calculate u double dot at time step 0 as such that m inverse minus f naught minus k through this relation, right, because our original equation is, what is our original equation? M2 u double dot plus k u is equal to f. So, I use the same equation and so this should be, so I use the same equation to calculate acceleration at time t is equal to 0. I plug these values, so this acceleration, velocity and u u prime, u dot and the acceleration into this equation, and then using that approach I find u1 in terms of u0, u0 dot and u0 double dot. Okay. Then I go to the next time step, I calculate u2 in terms of u1, u1 dot, u1 double dot, and so on and so forth. So, this is how I keep on marching forward in time. And the last thing is that at the end of each time step, so suppose I have calculated u1, then I have to calculate, for the next time step I have to calculate velocities and accelerations. So, I calculate that and I march forward and I keep on marching forward, and our solutions will be stable if we use these two values of gamma and alpha. They may be conditionally stable if I use these two, one of these two sets of alpha and gamma, provided my time increment is smaller than the critical time step which as calculated here. So, this is the conclusion of our today's discussion on hyperbolic equations, and in tomorrow's lecture we will close the entire discussion on FEA, but before that we will also cover two small topics known as explicit method and implicit method. So, with that we conclude for today, and we will meet once again tomorrow. So, thank you very much. Bye.